get us, hopefully if we have enough time, kind of chat in a bit, to a position where we basically can start really looking at a quantum mechanical system, and one that is relevant to chemistry. We just got a little bit more math work to do, and all we're gonna find when we do that math work, that the solution that we want for this problem is kind of fall out just naturally from the work that we do. And it might not be immediately clear exactly why it's chemically relevant, but I'll certainly convince you by the end of the module that our results will be chemically relevant. So let's step back to where we were. We've derived, I've kind of convinced you that we've been talking about measurements. We've talked about the state, which is the wave function, right? It represents this molecule or this atom or this electron. It has certain properties that, again, I'll review as we come up to them. But we're really focusing on things that we can measure. The boxes, the color box, the flavor box, the actual measurements themselves, and how are they represented mathematically. And we came up with this idea of an operator, right? I claimed that these boxes, measurement boxes, can be represented by a mathematical object called linear operator. And we introduced last class two different kinds. Very simple. Well, we started with position, right? We talked about position a lot. I think it's important because we're going to be asking a lot of questions about position. Because ultimately, we're going to think about chemical structure. What is chemical structure? Well, it's something about the average position of electrons orbiting a bunch of nuclei, right? So we're going to want to think about the positions of electrons. That's chemical structure. So chemical structure is inbuilt. We can build chemical structure through position. But objects move too. Electrons orbit. They might, or atoms may move from one part of a box to another. Right? So we need to think about their momentum. And I described why we choose momentum over velocity. The reason why is velocity is not conserved. And the velocity of a moving object depends on your point of view. Right? Velocity looks different to someone co-moving with an object versus someone who's standing still. But momentums are conserved. Right? You'll read out the same momentums for every object, regardless of how you're moving. You can always rederive the original momentum. Right? So the conservation of momentum is a hard one for us. And so we should talk about momentum when we want to think about motion. Okay, we're going to stop thinking about velocity. Velocity is undefined for us. Then we'll think about momentum. And I came up with this operator, right? We saw that the operator for the position is just adding x, just multiplying our wave function by x, right? We'll look at an example of that. So we have this, we put this wave function out there. We say x times the wave function will give me the position of the wave function, or the position of the particle times the original particle. But the momentum says, hey, if I want to measure the momentum, I have to take the derivative of the wave function and multiply it by this minus IH bar by h, where h is a constant I haven't defined yet. It's a number, right? Let's look at that number today. That number is super important in this class. We'll define it today, and we'll be able to understand what that number is using this definition. Right? So it's kind of a weird structure. This derivative and this I, who the hell knows? But let's work through it a little bit, and get a sense. Let's just kind of accept it as true and kind of work with it with our math. Okay, and see where we can lead, where it leads us to. Right? Maybe we'll have a better appreciation of this formula once we kind of start looking at results using. So let's do that. So what do I want to? Ultimately, though, I don't really care. I mean, I care about position of an electron orbiting a proton in a hydrogen atom. That's important. Its momentum is important. But ultimately, we want to think about things that we can measure in time. Right? Maybe we want to watch a reaction go. Right? That's going to have some time component to it. Right? And so, just like with momentum, we chose momentum as a measurement because momentum is the same regardless of where you are in space and how you're moving relative to those things that have momentum that you're monitoring or measuring. We need something that gives us the same result for that process, regardless of when we measure. Right? So if I do a measurement now and I see something happen in my system, I want something, a number that I can track, something I can measure, that when I do it a day later, I get the same result. Right, so I want something conserved in time, but something that I can reproduce in time every time this process happens. And maybe that process is simple as the particle moving from here to here. Right? It's a very simple thing, right? I want to make sure I have something that I can measure that doesn't change with time. Right? And the thing that doesn't change with time, the quantity that's conserved in time is energy. Energy is the thing that no matter when you measure a certain process, the energy will always read out the same, regardless of time measure. So we want to think about how to construct an energy operator. We want to measure the energy. That would be really, really useful, especially since we took this class last semester. We talked about energy all the time. That was our number one priority, was to define the energy. So maybe it's good to define the energy of our particle. So let's do that today. We're going to find that once we write down the energy, we can really start thinking about these particles very explicitly. So let's think about energy. I'm going to keep this table open for now, and I'm just going to write below it a bit and just make some notes. Because we'll come back and fill it. Okay, so we're going to use now we can use the way that Newton does energy, which is you take F equals ma. The force is the addition derivative with respect to the potential energy. I'm not going to do that in this class. Instead, we're going to do something very, very simple. We're going to define a quantity called the total energy. All right, and we're just going to add up all the energies. All right, we're not going to think about anything else. So define the total energy of our system. We're going to give it a special label. It's not going to be E, it's going to be H. I'll explain why in a second why it's H, which is the sum of the particle's kinetic energy, which I'll call T. It's a convention. What we call translational energy, which is why the T, and potential energy. V. All right, so the total energy H, just a number. We can split into two parts: the kinetic energy, which is the translational energy, the energy of the particle moving in space, right? Its velocity, and its potential energy. So we have these two terms that we need to determine for our particle. And so let's go ahead and write down in our table, let's write kinetic energy, right? So that might be useful. Now, what is kinetic energy from just classic kinetic energy? Well, it's 1/2 times the mass velocity squared, 1/2 mv squared. I'll just write that here. This is the classical energy, kinetic energy. Well, we don't want to use velocities in this class, right? I explain why. Velocities aren't conserved. They depend on your point of view. So, but we have an m and a v in here. Well, we can replace m and v with momentum in here. Right? We could do a little bit of algebra to get rid of the v and replace it with a p. All right, it's not too hard to see that when you do that, you get p squared over 2m. Because mv is p, we get a factor of p times v. V is p over m, so you get p squared over 2m. All right, well, that's nice. Now we have this really nice relationship between something we know and something that we can calculate, right? That the kinetic energy is dependent on the square of the momentum. And we have an operator for momentum, right? So we should be able to define an operator, so a box, if you will, a mathematical box, for us to measure the kinetic energy of our particle by using the momentum box. So let's see kind of roughly how that math works. And again, I'm going to write. Let's just write notes here. So what we can say now is our kinetic energy operator T hat is the momentum operator squared over 2 times the mass of the particle. Well, what is the momentum operator squared, right? Well, we can just write that as P times P. Right? It's the momentum operator twice divided by 2. All right, so if we have a box that measures the momentum of our system, if we know the mass of the object, all we have to do is run the particle through the momentum box twice, read out the readout from that, and then divide it by 2 times the mass. Now, it may not be clear to you immediately why I have to run. Why is it that when I run it through 2 momentum boxes simultaneously, right? I put one particle in through one, the output goes into this one. Run it twice, and that somehow gives me something proportional to the energy. That's just how the math works. Right? This is just how the math works out. So there's not really an explanation why it is. It just is. And so what we can do now is we can write a momentum operator in terms of 2 operators operating on our system. Right? We can measure P once on side and then measure it again on the output. And that just works out algebraically as if we were just squaring the P operator. Right? So this is 1 over 2m times minus IH bar d by dx squared. Well, we can do some math here. The minus signs cancel out. Right? Minus 1 squared is 1. I squared is minus 1, so we get a minus sign back. We have a 2m. So that's 8 minus h bar squared over 2m. And then we have the square of the derivative operator. Well, that's just the derivative operator operating on the derivative. So it's a derivative of a derivative, which is just the second derivative. So now we have, I'm just going to kind of summarize this nicely. The energy operator for kinetic energy is just minus h bar squared over 2m. These are numbers. Times the second derivative with respect to position. All right, now when you look at this, you're like, well, what the hell does that mean? All right, but remember, this is an operation. Right? So it's a box that we stick a wave function into, and it does something to it, and it should output a number, which is the eigenvalue, right? The measurement result, just a real number, times the original wave function, just like our color box. And so let's think a little bit about the math of this operator operating on a generic wave function. So let's think about that. So let's consider a particle such that when I measure the kinetic energy of it, T psi, I get back some energy T sub E, that's the kinetic energy, times psi. Right, so this is my particle, my atom, and this is the observed kinetic energy. So let's just sup in our operator in here and see what that math looks like. We get an equation, right? We get an equation that says something of psi is equal to a number times psi. Right, so we have minus h bar squared over 2m times the second derivative. Right, that's the T operator, and it's operating on the wave function, right? So that means that the wave function
is getting its second derivative taken care of here. Okay? So we have the second derivative of the wave function is equal to some number times the wave function. All right, so what all this is saying is that whatever wave function satisfies this, right, whatever system satisfies this equation, its wave function, that when you take the second derivative of it, which is a function, that you get the same function back times time. Let me just rearrange that to kind of drive that point home. Right, I could write this as the second derivative of the wave function, whatever that function is, with respect to position, is 2 times the energy times the mass over h bar squared minus times psi. Right, so this just says that whatever function satisfies this expression, which is a valid wave function for our system, satisfies the property that when you take the second derivative of it, you get the same wave function back times some numbers. Well, there's only a few functions in the world that satisfy this property. It's a function that when you take the derivative twice, you get the same function back. All right, so obviously psi can't be a polynomial like x squared, x to the third, right? Because every time you take a derivative, it gets one order less. Right, so psi can't be x cubed. The second derivative is x. Obviously, don't get the same function. All right, so it has to be some function that when you take a derivative of it, it just returns the same thing, or maybe it oscillates between two values or something like that. Something that you take derivative twice and it comes back. So there's only effectively 3 options. Right, so some options for psi. We can just kind of reason them out. All right, so the first one, and I think this is probably one that you'll think of, is psi is equal to e to the kx, where k is a number. Right, obviously, when you take the derivative of e, the x, you get e to the x back. As you take 2 derivatives, e to the x. Great. So we know that probably works. Right, so let's think about that. We can solve what k is by taking some derivatives. The first derivative of psi is k e to the kx. And the second derivative is k squared e to the kx. Right, and that means then that k squared is equal to minus 2 times the energy, m over h bar squared. And that means then that k think about this. It's got to be, but this doesn't work. This can't work. The reason why this can't work is because this has to be positive. Does it have to be positive? Yeah, it has to be positive. You take the square root, you get k is equal to the square root of minus 2 times an energy mass over h squared. These are all positive numbers, so it's a negative, so that can't work. Right? So this leads to an imaginary result. K is not real. No solution for k. All right, and even if that didn't work, if we think about it, imagine now we have this, let's just think what this wave function would look like on the x-axis, from x equals 0. This just grows and grows and grows and grows and grows. I'm sorry, it starts from 1. Sorry, let me start that over. Right, e to the 0 is 1. So the value starts from 1 and grows exponentially. Like that. That should be psi. Right? And remember that we have a specific constraint for our wave function. The constraint is that the integral over the entire space of the box, which will be infinity to minus infinity, of our wave function squared, which is e to the 2kx dx. Well, what's this integral? Well, it's infinity. Let me write this constraint, right? So the integral of psi squared is infinite, but we know that by law that the integral of psi squared must be equal to 1. This is our constraint. So even if we can massage the coefficients around to get this to work, the integral of this function squared, which should equal 1, it should converge to a number, doesn't, because e of x just blows up. It just blows up. Right? So this never works. Okay, so it can't be e to the kx. Right? Just by definition, right? The function has to integrate to a value. This doesn't integrate to a value, it just goes to infinity. So we can't use this function. All right, so let's try another function that returns the same function after two derivatives, sine or cosine. I'll just pick one. It doesn't matter which one we pick. We'll get the same result. What about sine of kx? Well, let's calculate the derivatives. The first derivative is cosine, k. Let me just erase that and clean it up. It's k times the cosine of kx. And then the second derivative is k squared. Minus k squared sine of kx. Okay, so that one works. We take the second derivative, we get sine back times a number. Now we have a nice negative sign there, so we can solve for k. K is equal to 2 times the mass times the energy over h bar squared. I haven't defined h bar squared yet, but we'll get to it in just a minute. Just remember, it's just a number. Okay, so that seems to work pretty well. All right. We've got some number that comes out, satisfies the expression that we need for the operator. It gives us the function back. Everything seems to be pretty good so far. But here's the issue with this function. Is again, let's think about our particle on a line starting at x equals 0. Again, think of the room. All right, I haven't defined any wall. All I've said is this particle is basically free to move wherever it wants, right? It just has kinetic energy. So I haven't defined a space at all. As far as I can tell, it's in an infinite vacuum. Right? I haven't said, hey, there's a wall on this end, there's a wall on that end. Right? I just said, hey, we've got an open box, no ends to it. Just have this atom sitting in the middle of this box that's allowed to propagate wherever. So what does the wave function look like for this box? Well, the wave function is the sine. So psi just looks like a sine wave. All right. Well, let's apply now the previous constraints, right? We want to now integrate the square of this wave function, which is sine squared, across the entire space of my box. I haven't defined my box. Box is infinite. It's a totally free particle. So we now have a wave function squared. This is psi. And I'll just draw right here in a different color what psi squared looks like. This is what psi squared looks like. right? And we need to integrate this across the entire box, which is infinite, right? So the integral is going to be this peak, 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 ad infinitum. This is the integral of psi squared over dx, right? And this is going to be taken from infinity to minus infinity, right? Because the box is infinite. Does this converge to a value? No, because over infinity, there is a hump every half period, and every single one gives you a positive integral, and there's an infinite number of them. So this doesn't work either. Right? This is infinity. No good. Okay, so we found a function that satisfies our differential equation, the equation for the function. Second derivative is equal to the function, but it doesn't satisfy the integral property, right? Remember the wave function tells you about probabilities. So the total probability of finding a particle anywhere has to be 1. Right? And that means that the integral of the function over the entire possibility of places for the particle to be has to be 1. And the fact of the matter is there's infinite places for it to be, so the integral is infinite. Right? There's one option, one less option. We've already seen it. Right, so the third option and the final option is this function AE to the IKX. Right, and we saw that this is A cosine KX plus I sine KX. All right, so now what we have again is a sine wave. Again, it's like the other function that we have, the one that we just looked at, but this is now a complex function, right? So it's got longitudinal oscillations, cosine wave, and transverse oscillations in the other plane, the imaginary sine. All right, so we have this two-dimensional waves now. It's got two propagation vectors, transverse and the longitudinal. Right, whereas the other guess was just one of them. Right, it was just the sine part, the real part. Right, and if we chose cosine, we get the same answer too. So now what I'm doing is combining them together and adding an I, making it complex. All right, so let's look again. Let's do the same analysis. So the derivative of sine, of psi, is I K A e to the I K X. And the second derivative is, again, not too hard to calculate. We get another factor of I coming down, so we get a -1 K squared A e to the IKX. Okay, so that satisfies our property, right? We take the derivative twice and we get the same function back times a number. And this says that K squared is equal to, let me get it right, 2m t sub e h bar squared. Kinetic energy. Right, and that's totally okay. That's good. And now let's look at the function. Let's do the integral calculation, right? We need to make sure that it's convergent, that it gives me a finite probability, all the possible choices. Well, again, let's go back to the way we looked at this function, right? It's not appropriate to think about this in real, right? To think about the real component, we need to think about the real and the imaginary components together simultaneously. Kx, if you think, is like an angle. Right? It's not a position, but an angle in this case, right? It tells you something about the direction in the imaginary plane that this wave or the phase of this wave is pointing towards. So, right, so we have a two-dimensional graph now where we have the real part of psi and the imaginary part of psi. Remember, the real part is the longitudinal part, and this is the imaginary part, the component on the eye. And then we're going to track this as a function of x, right? You just form a circle. We saw this last class. Right? As x increases, this goes around in a circle. So what happens to this wave as the system in real space is, again, we can think of it as moving across. It's doing something in the box physically, moving in some ways. However that looks, I'm not sure yet. But what the system is actually doing functionally is circling over and over again around the circle, right? I complete one circle and the function recalls, if you will, revisits the same values every single rotation. Right, so I go through every possible value of this wave function through one oscillation, and then I go through them again. And then I go through it again. And I'm just sampling the same space over and over and over and over again. Right, so the integral of this function, right, so we could think about calculating from negative infinity to infinity of our wave function squared dx. But if we do this in complex space, if we track the function in complex space, all we're doing is going in a circle over and over again. Right? Instead of what's an oscillation, a hump, and a wave on the x-axis in real space, we're actually doing complex space just going in a circle. Same thing over and over again every 2 pi great points. Right. So when we actually are integrating, all we're doing is calculating the area of this circle. Right. So this is the same as 0 to pi psi. Well, it's an imaginary, so we need to write psi star psi dx. Right. And that is just the area inside the circle. Right. And that's finite. Right. It's what's the surface area of a circle? Pi r squared. Is that right? Pi r squared, right? So this has area pi. Right. So we can actually write a wave function that's normalized. We could say psi of x, and this is how it works out, 1 over square root of pi e to the I kx. This satisfies all of our properties. It integrates to a finite value by considering it complex space. It gives me the second derivative when I measure the energy and gives me the function back. It does everything I want. Right? But it's necessarily complex, right? This is the proof that the real life is complex. The only thing that satisfies our system, and what we have is anything you can think of. It can be a photon, it can be an atom, it can be a molecule, an electron, just a single object floating in this infinite box by itself. Right? Doesn't matter what it is. The only reasonable representation that satisfies all the properties that we know so far is this complex wave. It has to be complex. Has to be. Right, so this is where complex numbers, so I never will call them imaginary numbers unless I have to, because this isn't imaginary, this is real. Right? Now I'm going to show you something very interesting, and this will tell us something about this H bar number, why I know that this has to be the case. Well, first of all, we've already seen it to be the case that there is this wave-like behavior for everything, so we would expect a wave-like function. But let's do some analysis of this a bit. Do some analysis of this and see what we get out. All right, so we have these new magical functions. So this is what we call the wave function for a free particle. All right, we'll look at the let's look at some properties of this particle. All right, well, first let's measure the kinetic energy. Well, that's going to be minus h bar squared over 2m times the second derivative of psi with respect to x. Okay, so that's minus h bar squared over 2m times the second derivative of 1 over the square root of pi e to the ikx. Right? So now we're just going to calculate the kinetic energy of this particle with component k. Okay, well, it's just a very simple math, right? We just have to calculate some derivatives. Let's factor out the pi. Well, let's just leave in the pi, actually. So let's do a derivative. So we have minus h bar squared on over 2m. I'll put the 1 over square root of pi here, because we can factor out the derivative. And the derivative of e to the ikx is k squared e to the ikx, right? Because the minus. We get two factors of I down, that's -1, two factors of k, that's minus ikx. So minus k squared e to the ikx. Okay, and we know, so remember that the rule that we want is that the operator returns the original wave function times the energy. So the original wave function I'll underline is this e to the ikx and this 1 over the square root of pi. So the kinetic energy is everything that's left over. So that's going to be, so the minus signs cancel out. We're left with h bar squared k squared over 2m. All right, so this is the kinetic energy of our free particle. But we've got some things to think about. Well, the energy has to do with the mass, has to do with this constant h, it has to do with this value k. All right, what is k? Well, k can be anything. I haven't made any we haven't made any claims about what k is. It's just a number. All right, so I could plug in any number to k, and I get an energy. There's no limit to what k is. All right, so let's think now. So what that means is that the energy of this system is a function of k. So the kinetic energy is a function of this value k, and it's h bar squared over 2m times k squared. Right. I've just arranged a few things, right? And k could be anything. Right. So if I were to plot k versus the kinetic energy of the system, well, the energy of a particle not moved with no k, 0k is no momentum, no energy, so it's 0. And the energy just increases quadratically, right? It increases as k squared. Right? And you can have any value you want, right? It can be here, it can be here, it can be here, it can be here, it can be in between. Right? So this has a continuous set of energies. Right? A free particle can be any energy it wants. That should make sense to you. You throw it, right? It's just like a ball, right? You can throw a ball at any initial momentum or any initial energy you want. That's me. Right? So the kinetic energy of this free particle isn't any different. Right? So k can be any value. Right? Let's do just a bit more analysis here. We can remember we can relate the kinetic energy to the momentum. Right? Remember the momentum is p squared over 2m. Right? So note, how are we doing? 10 minutes. Great. We can write t as p squared over 2m. And in this case, that's equal to h bar squared k squared over 2m. Right? And this says that therefore the momentum of my particle, the absolute value of my momentum, is h bar k. So my momentum is dependent on K, and it gives me, this H bar gives me some units. Remember, K is just a number. It's just a number, right? It's 1, 2, 3, 4, 4.5, 69, whatever you want it to be. Pi, E, whatever it wants to be. So the momentum is this value K, some unit, some value, times this H bar, right? Which is a fundamental constant of the universe. Right? And so let's, for the last 10 minutes, let's just stop for a second and think about this equation. All right, so what this is telling me is that, and so let's think about K. K, right? K is like a frequency, right? Because the wave function is cosine kx plus I sine kx, right? So K is like a frequency of a wave. It's how fast the wave is oscillating. Well, the faster the wave is oscillating, the shorter its wavelength, if you will. Or the faster it's oscillating, the higher its energy, or whatever you want to think about it, the higher K is. Right? And because it's equal to the frequency of a wave, we could write K, if it's moving at the speed of light, as C over lambda. Right? This is the wavelength of a light. Right? And C is the speed of light. 299,792,458 meters per second. All right, so what that says is that for light, a light particle, a light wave, that its momentum is equal to h, this value hc, over its wavelength. So the longer, what this is telling me is that from this perspective, light, you know, as you see as a wave, right? This thing is emitting light waves, this light here. That the light waves have a characteristic frequency or wavelength, right? These are in the, this is a white light, so it's emitting a lot of wavelengths, but let's say 400 nanometers. Some blue light, some green light. It says that if you're emitting this light, that the wave has some characteristic momentum. That the wave, this light is carrying momentum like a particle. You can, now we can't prove this ourselves, but you can see this, the proof of this in experiments. And there's a really, really beautiful way to see this. What this is telling me is that if you have an object that's floating freely in space, okay? Imagine a piece of aluminum foil that's completely stretched out, a square piece of aluminum foil that's just floating in space by itself. Right? And then what you do is you turn a light source, say a laser, and you point the laser at it. And it's, we draw it on the board. Do I have time? Good, I do have time for this explanation. So imagine you have my luck with that. Here it goes. Imagine you have this piece of foil that's floating in space that has some mass, called mass of the paper. It's just some aluminum foil or something like that. And what I'm going to do is I'm going to shine a laser at it. Some wavelength. And this is initially, the momentum of the paper is 0. Okay, so it's just floating in space. You turn this laser on, let's say for a minute, right, at some wavelength. And you shine this laser at this paper, it absorbs, imagine it absorbs all the light, doesn't reflect it, right? It's perfectly absorbed. Right, so it absorbs all that light. What you will see is that after radiation by N photons, you'll find that the momentum As I mentioned, you can count the number of light particles that go through. You can do that. It's not that hard to do. You know how of the energy and how long it's on, you can count the number of photons. The momentum of the paper starts moving. And it moves by n h bar c over lambda. Each one of those photons imparts some energy as momentum into the particle, into the paper, and the paper starts moving. If you have the wavelength, which means double the frequency, right? So it's twice as powerful, also twice as fast. The new momentum that you observe on the paper is 2 times the momentum that you had before. The other thing. So if you go from 800 nanometers to 400 nanometers, your aluminum foil will move twice as fast after that number of photons. Right? So the light particle is literally imparting mechanical energy, mechanical momentum into this physical object and causing it to move. Right? This is seen with satellites. Here's a really great example. There's 2 satellites that were launched in the early 70s called the Voyager probes. Do I have time to show you? I do. Let me show you where they're at right now. I won't have time to show you the curves that I want to talk about, but I can show you where these are. All right, these are the 2, the Voyager probes are the 2 furthest objects that man has ever sent. Right? They're further than anything we've ever sent in our history. I need to find a really good picture of it. Okay, here's a good picture of it. That's not the scale. I hate that. Please give me something to scale. Ah, beautiful picture. Beautiful picture. Exactly what I want. Oh my God, it's like super low res. Come on. Ah, yeah, here we go. Here we go. Thank you, Google. Okay. So here's the 2 Voyager probes. They are officially out of the solar system. All right, well, I already talked about the Voyager probes in the problem set, but so they're all the way out here. All right, so they're finally passing heliopause. There's a shock wave at the edge of the solar system from the solar winds, and there's a hard cutoff. There's a shell that the sun creates from its energy. It's called the termination shock of the heliopause, and everything else out there is just space, literally space. There's a different meteorology, like you move from one biosphere to another in terms of its conditions. So anyway, Voyager 1 and Voyager 2 are gone at this point, very, very far away. They have just enough power that they can communicate they can ping back and forth. We can triangulate their positions. Right? They're running out of energy. They have plutonium reactors on them. They're running out of energy. Actually, they're running out of cooling material. They have liquid helium that cools them. They're running out of liquid helium. And so what you can do, because you can track them, you can watch their motion curves. You can watch how fast they're moving and how fast they're accelerating or decelerating. And what people have, what the Voyager people have noticed is that as the Voyager started to move away from Earth continuously, they were accelerating. They're getting faster and faster and faster. Right? They get faster and faster and faster. And so they're accelerating, they're moving faster and faster every year until they hit a certain point. And that point is, it turns out, is where the drag associated, again, there's some particles in space, or some hydrogen atoms, some protons, all sorts of little small things. They induce drag, right? So you have some drag from some air-like material this way that's trying to slow the Voyager going out this way, right? Some friction, some heat. So it's not perfectly empty. All right, so there's this effect of friction trying to slow the Voyagers down, right? So you would think that they would slow down, but they were getting faster, right? So there has to be something pushing them. Well, what's pushing them? Well, the claim is that what's pushing them are the photons from the sun, right? Each photon from the sun imparts some amount of momentum. And so when they were really close to the sun, they were receiving on their solar panels, which are big, broad things like this, right? They're really, really wide out, some momentum from the sun. Sun was giving them a boost, a momentum boost from the light. Eventually, though, the intensity of the light from the sun goes as 1 over the distance squared. So by the time they get to twice that distance originally, they now have 4 times as much light, 4 times less. So they impart 4 times less momentum after that motion. And what you find is that as these Voyagers are starting to come towards the limit of where the sun's effects are, and starting to come into the interstellar cloud, that friction from the particles moving against the Voyager are starting to win out. Because the flux of photons from the sun is starting to decrease in 1 over r squared, it's no longer imparting as much momentum. So now, as of in the last 10 to 15 years or so, the Voyager crafts, they aren't slowing down, but they're deaccelerating. So they're not speeding up as fast as they used to, right? They're starting to coast, right? And the reason why is because they're now no longer getting a boost anymore from the sun. Not enough photons to push them. Right? So, and NASA has designs for this called solar sails. They're giant pieces of this fabric that is highly absorptive and reflective of electrons and different particles and light and stuff like that. And big light blue sails that collect all that energy from the sun, both highly energetic particles and light, to push the satellites along with this natural source of energy, the imparting of momentum from microscopic particles and light, just like we've discussed here. And in fact, the calculations show that if you get this done right, you can get a really nice cloth sail, and you get the trajectory just right. The calculations are that by the time the solar sail satellite hits the point where Voyager's at, it's already moving at 1/10 of the speed of light. And so the energy of the sun imparts a significant amount of momentum. Right? You just got to learn how to collect it efficiently. Right? And all light does this. All right. So the drive home point I want to get to this is that particles, light, they're different, but they have the same properties. And the fact of the matter is that it doesn't matter if it's a massive particle like a proton or an atom or a molecule, or a massless particle like light, right? Light does not have mass, yet it still imparts an energy like a particle. It collides with something and imparts momentum. And that's true for things that have mass as well. Things with mass impart momentum like a mass, but they propagate like a wave. Right? Light propagates like a wave that imparts mass, momentum like a mass. Okay? So these things are interconnected. Light isn't really so much different from massive particles like atoms, and they satisfy the same physics and the same types of behavior. Okay, so we'll look at that more carefully on Wednesday. What we'll do is we'll take our box and make it finite next. Put some walls in and see what happens next. Right, and then you'll find that when we add walls to our box, things get very interesting very fast. Okay, so we'll study these walls, and then we'll be able to start doing chemistry with it. All right, guys, have a good one. Oh, I forgot to write what H is. I guess I'll do that next class. Damn it. You don't need it yet. Next problem set. Yeah, we'll measure it next class.
2 minutes in between. Let's put that and walk there. But the third class too. Yeah, and so I'm almost done because I just have that one and then